Okay, we are looking at a review topic from about 5 months ago. It was December, if I remember correctly, when we went over similarity and dimension changes. So you could actually probably flip back in your notes if you're a decent note taker. There were 2 days that we worked on similarity in multiple dimensions, and then the next day we did proportions in multiple dimensions. I am not going to break a review down into 2 different days worth of information, so I just kind of condensed it a little bit, consolidated it into one lesson, which I'm going to go through really fairly quickly, and then we'll have an assignment to go with it. And again, we're reviewing this information because C-Scope has continued to ask us question after question after question dealing with dimensionality issues, questions that are similar to, hey, if we've got a particular figure and then we change all of these side links by a factor of 3, then they ask questions like what kind of an effect would that have on the surface area, or what kind of an effect would that have on the volume? And quite frankly, we simply have not had good answers for those questions. Okay, it seems pretty clear that we're probably going to face at least some questions like that on our test on Thursday, since we have been dealing with calculations that have existed in 2 different dimensions: surface area in the second dimension, volume in the third dimension. So let's have a look back at what we did. Okay, this is kind of the basis for what everything all these dimensionality issues. This is what it's all based on right here. And we discovered these ratios again back in December. Okay, so the ratios of similar figures always follow, and it's not really a pattern, it's pretty much a rule. Okay, and the rule would state that whatever your scale factor is doing, and of course a scale factor is a direct relationship between one figure and a similar figure. Okay, and that would suggest when we were doing it, that was like we were comparing one polygon to a different polygon. That may not be the case on the type of questions we've been seeing here lately. We may not be comparing a rectangle to a bigger rectangle, or a pyramid to a bigger pyramid. Instead, what we may be doing is saying, hey, I've got this rectangle or I've got this pyramid, and then they propose some type of a hypothetical change. What would happen if we did this to that shape? So it may be, instead of comparing one shape to another shape, comparing one shape to the exact same shape based upon the change that they're talking about. Okay, but anyway, what we kind of discovered is that every measurement that was in the first dimension, okay, the ratio, the relationship between those ratios would remain unchanged. For example, if we took a figure and said, okay, let's double all of the side lengths, which would be linear measures, what kind of an effect would that have on perimeter? Well, since linear measures and perimeter are both first dimensional measurements, okay, well, if you double one of them, it's going to double the other one, okay, since they're in the same dimension with each other. But when you start comparing things like, all right, we've got this figure, we're going to double the side lengths, well, what kind of a change would that have on the area of the figure? Okay, well, if you double something in the first dimension, that doesn't mean it doubles in the second dimension or doubles in the third dimension. It makes some different kinds of changes as we change from one dimension to another dimension. Okay, and as you can see from the ratios that are on the board, and again, this was from back in December. Okay, linear measures and perimeters remain unchanged. Okay, but area, since it switches from the first dimension to the second dimension, okay, see the ratio up there, a squared to b squared. That means that whatever change is being made, that change is going to be squared as it switches from the first dimension to the second dimension. So if we say the side lengths are doubled, and then say, what would that do to area? Okay, well, doubled means times 2. But going from first dimension to second dimension causes us to square the amount that it's being changed. So instead of just multiplying by 2, it's multiplying by 2 squared, which is 4. So if you double the side lengths, okay, then it actually quadruples the area, okay, 2 squared. And as far as volume, you've got the same type of theory, but of course, volume is a third dimensional measurement. So if we do something in the first dimension, like double all the side lengths, then the question says, what would be the resulting effect on the volume of the figure? Well, going from first dimension to third dimension causes us to have to cube things. So if you double in the first dimension, that's times 2, but going to the third dimension also causes us to take that 2 and cube it. So you got 2 times 2 times 2, which would be 8. Okay, so if you double something in the first dimension, that means it's multiplied by a factor of 8 in the third dimension. And if you can accept that that is just how things are going to work as you change dimensions, then there's really very little that these questions can do to you that'll cause you to miss them. Okay, so the rest of this ought to be kind of restating what I've already said here before. Here was an example. Two similar solids have a scale factor of 2 to 3. Scale factor is a first dimensional measurement because it relates to side lengths. Okay, so if they say, all right, we got a scale factor of 2 to 3, what would that cause the ratio of the side lengths to be? Well, I already gave that one away because scale factor is a first dimensional measurement which is based upon another first dimensional measurement, side lengths. So if the scale factor is 2 to 3, what's the ratio of the side lengths? Also 2 to 3 because they're both first dimension. What if I changed the question and said, all right, what is the ratio of the perimeters of the bases for these figures? Okay, well, what dimension is perimeter in? Yeah, it's still a first dimensional measurement. So the same ratio that applied for scale factor and also applied for side lengths is going to still apply for the ratio of their perimeters. Does this say, I mean, saying that they're all 2 to 3, does it say that those are the actual values? The perimeter is 2 and the side lengths are 2 and the scale factor is 2? No, that's just the ratio that they're in. They're in a 2 to 3 ratio. Okay, so the perimeters and the side lengths and the scale factor, they may be much bigger numbers than 2 to 3, but this is the relationship between those two. Okay, and if we change the question even further and say, okay, based upon the information that's going on here, what is the ratio of the surface areas of these two solids? Okay, well, what kind of dimension is surface area in? Uh-oh. Yeah, second dimensional measurement. Okay, area is second dimensional, which means this 2 that exists for one of the figures and this 3 that exists for the other figure, those both need to be squared to get this ratio, which was first dimension, up into the second dimension. So 2 squared and 3 squared. What's 2 squared? 4, and 3 squared? 9. Okay, so that's the ratio of their surface areas. That doesn't mean that the surface area of one figure is 4 and the surface area of the other figure is 9. They're just in that relationship, that ratio. Okay, and finally, we could say, all right, what about the ratio of the volumes of these particular solids? Well, what dimension is volume in? It's a third dimensional measurement. So this 2 to 3 ratio, which is a first dimensional ratio, you're going to have to cube the 2 and cube the 3 in order to find out what that ratio means in the third dimension. Well, what's 2 cubed? 2 times 2 times 2, 8. And 3 cubed, 3 times 3 times 3, okay, it's 27. Okay, there you go. That ratio is an 8 to 27 relationship in the third dimension. Now, okay, it's great that this is how this works, okay, but as we were going to see and we have seen before, is a lot of times we don't have a ratio necessarily handed to us that we're going to work with, so we can just cube it or square it or whatever like we were doing right here. A lot of times, including the problems that we have been seeing here lately, we have some type of maybe a volume or something like that, and we'll get to that here in a moment. Okay, and I had another one we can roll through here real quick. Okay, the following tetrahedron, and we've seen tetrahedron throughout the year, 4 regular triangles as their sides, is going to be similar to another tetrahedron. Scale factor between them is 1 to 2. Okay, so if the scale factor is 1 to 2, what's the ratio of their side lengths? Okay, scale factor is 1 to 2. What's going to be the ratio? comparing their side lengths. Also 1 to 2. Okay, what's going to be the ratio of the perimeters of their bases? Still 1 to 2. What's going to be the ratio of the surface areas? 1 squared to 2 squared. Okay, it'd be a 1 to 4. Okay, what would be the ratio of their volumes? Okay, 1 cubed, 2 cubed, 1 to 8. Okay, this is really fairly straightforward. All you have to know is which measurements fit into which dimensions. Okay. Now, if proportions come into play, we have to make sure that both sides of our proportion are in the same dimension. And this is kind of what the questions have been based on here lately. Not necessarily the proportion, but the same idea. Hypothetically, if we changed this one piece of information in this proportion, what would that do to the other parts of the proportion? That's what the kind of, to boil it down, that's what we've been seeing here on the questions here lately. Okay. And the answer is if one part of the proportion wants to change dimensions, that's fine. We have to make sure that the proportion matches in its dimensions. And the easiest thing for us to do is make the smallest dimension match the larger. So here was an example, and these are again, these are examples that we went over back in December. Okay, so again, if you have your notes, that's fine. If I'm going too fast, you can always watch this on Edmodo later. Okay, two similar figures have corresponding side lengths of 2 to 3. The first one's area is 36. What is the area of the second? Okay, well, setting up the proportion based upon the information, here's the kind of setup that we might have. The problem established itself on side lengths as being a 2 to 3 relationship, so I've got that 2/3 ratio in there. And then it talked about the first figure's area being 36, but then did not provide us with information about the second area. Okay, so that's what we got. We got 2 to 3 from one figure to the other, and we got 36 to unknown from one figure to the other. Okay. At this point in time, here's where we start getting into the important stuff. Trying to decide, is this a good proportion or not? Is there a dimension change to consider or no? And that's what the problems have been asking you about here lately. Hey, we're going to change this thing in one dimension. What does that do over here on this other measurement? Did it change anything? Yes or no? If it did, how did it change it? Stuff like that. Okay, so the consideration is in this case, we just said that a first dimensional measurement, which was the side lengths, 2 to 3, we said that that was equal to a second dimensional measurement, which was area. Okay, and the question is that true? Are we allowed to say the first dimension equals second dimension, or does this actually require an adjustment of some kind? Well, the first dimension does not equal the second dimension. Second dimension does not equal third. First does not equal third. They are all completely independent of each other. Okay, so this is an inaccurate statement. First dimension does not equal second dimension. And this is the kind of question when they say, hey, if we triple something in the first dimension, what does that do in the second dimension? If you say it triples, you just missed it because it changed dimensions between those two locations. We need to make an adjustment. Okay, now it comes down to the proportion. Okay, simply enough, what we're going to do is we're going to bring the smaller of the two dimensions up into the larger of the two dimensions. Okay, so since first dimension did not equal second, squaring the first dimensional ratio will bring us up into the second dimension. Now we have a true statement. Okay, 2 is to 3 as 36 is to x was inaccurate. 4 is to 9 as 36 is to x. That is an accurate statement. Okay, second dimension equals second dimension. Once the proportion is balanced, okay, as far as the dimensions are concerned, you can cross multiply and solve it just like normal. 4 times x is 4x, 36 times 9 is 324. You don't want 4x's, you just want 1, so divide that 4 out of there, and x is 81. Okay, so really very easy math once you get the dimension consideration out of your way. Okay, and this is more like the kind of questions that we've been seeing here on the C-scope tests here lately, and it seems that tomorrow or Thursday rather will probably be no exception. Okay, they've established that we have two spheres that are similar to each other, and it's fine. Like I said, it doesn't necessarily have to be two spheres that are similar to each other. The question could just as easily be going, hey, I've got a sphere, we're going to do this thing to it, and then examine what happens after that. Those are your two spheres, kind of the original one that they're talking about, and then the one that later. So kind of like the before and after. Those are your two shapes. Falling spheres are similar. Scale factor between them is 2 to 5. What is the volume of the figure on the left? Okay, well, you've got 2 to 5. That's one of your ratios. And we've got unknown volume is to 100. That's your other ratio that you have there. Before you go any further, we just go, okay, we need to see if this proportion is true or not. Okay, 2 to 5, that was scale factor. What dimension is scale factor in? Okay, it's in the first dimension. Okay, so that's kind of the beginning of the problem. That's where they might say, hey, we're thinking about changing the scale factor or the radius or the diameter or the great circle. We're thinking about changing it from a 2 to a 5. Okay, and then saying, okay, what would that do to the volume? Okay, well, let's have a look. Scale factor is a first dimensional ratio. We cannot say it equals a third dimensional ratio. So we'd have to cube that change, pardon me, cube that change in order to examine what it would actually do. Okay, well, we got some bigger numbers here. I think we know what 2 cubed is. 2 times 2 times 2, 8. 5 times 5 times 5. Okay, well, 5 times 5 is 25, and 5 of them would be 125. Okay. Now that the proportion is third dimension all the way across, we can really very easily find out what's going on. You've got 8 times 100, which is 800. 125 times x is 125 x's. We don't want 125 x's, we just want 1, so we divide everything by 125. And in this case, it goes in 6.4 times. So changing, 2 to 5 in the first dimension actually is like changing 1 to 6.4 in the third dimension. Okay, and that's the way these problems work. Okay, so again, this is review of stuff from back in December. We just have not done a very good job of dealing with it when we've seen it. So I found it to be probably important for us to spend a day working on it again. I do have an assignment that goes along with it. Okay, it is nothing new. It is the same as the assignment that I gave you back in December. So if you're determined to not do any work or learn about this, I'm sure you might be able to dig up the old assignment and copy the answers down. But of course, that won't help you as far as learning anything about this. So anyway, that'll be the last of the material that we're going to talk about going towards the Unit 10 test on Thursday. Tomorrow will be a review day, which actually will not take us much time at all. If you get to thinking about the kind of material that we've talked about in Unit 10, there's just not a lot to it. I mean, it's surface area and volume. We've basically been doing surface area and volume over and over and over again and working off of the formula chart pretty much exclusively. So there's not going to be a whole lot for us to really talk about. So you might want to come equipped with some questions, some things you'd like to see worked out. And that'll probably be the majority of the way our review will go on Wednesday. And our test will be on Thursday. So you definitely want to be preparing yourselves for that. The 6 weeks ends on Friday, and some of you are in need of a fairly enormous number on that test in order to survive the 5th 6 weeks. So that's that. Let's get to the assignment.